Hey, welcome to The Art of Code. My name is Martijn, and what you see behind me here is a weird looking alien creature that we've been working on for the last 2 videos, and yeah, so we got quite far. We did some soft shadows, we did some cool looking glitters that change when you move your mouse around. We did some blinding light that gets less blinding when something is obstructing it, and so that's all pretty cool. Now let's make some volumetric light around here that kind of shines through this structure here. So now in a lot of my effects I use a fake starburst pattern, and let me make that just to show you what that looks like. Okay, so this, here, let me just get this together here a little bit. So this is the center light, and this is the center light glare that you only see if you're looking straight into it and there's no obstruction, right? That's what gets kind of smaller here when you kind of obstruct it. Okay, center light glare. Also, by the way, it would be good maybe we should add some slight color to this. Let me go over here, say vector light call, and then let's make a color that is almost completely red. So let's say something like that. And now let's multiply that by that color, so times light call, and then over here for the glare as well, times light call. So it's still going to be mostly white, but it's going to have a tiny little bit of color on the edge, which is, I think, kind of cool. Alright, so but that's not what we're doing. We were going to do a starburst or a volumetrics, right? So volumetrics. So for the volumetrics, so what I normally do is I just use a trick, because most of the time your eye doesn't really pick up on whether it's exactly correct or not, and which is great because we can make use of that, because then we can get away with a cheaper effect that runs faster. So normally I do something like this, where I say, well, give me the polar coordinates of my UV coordinates. So polar coordinates, I did a video about that specifically. Check out the link in the description. But basically, just with this A10 here, I can get an angle from the center. Like imagine there's a clock in the center, and the hands of the clock, they make a certain angle with 12 o'clock, right? As you go around, it goes all the way to 2 pi around, and you can make use of that. And so that's what this A10 calculates. And then what I can do is I can say float SB for starburst, and I can throw that into a sign. So this actually, what comes out of here is something that goes from minus pi to pi, which is great because I can throw that right into a trig function, and it will loop correctly. So I can say A times some larger integer number. And let's see what that does. So col plus equals SB. So that gives me that. Okay, and then usually what I do is I multiply this by another sign, A times, and then usually I like to take prime numbers, because prime numbers, they don't easily fall on top of each other. Or do they fall on top of each other at all? I don't think so. So yeah. So like prime numbers like this is always good. So times the sine of A times 5, let's say. So that gives us a more complicated shape, and then I move the phases of these. If you move them counter each other, then the overall object doesn't rotate too much in one direction or another. So I could do say plus t minus t and plus t times 0.2, let's say. And that gives you something like this. And then if you if you just cut out the center. So I can do, say, SB times equals the smooth step of 0.5 to 1 with the center distance. Actually, I should make this smaller. Say 0.0 to 0.4. Then I can cut out the center. And this can often work quite well for volumetrics. It kind of makes it look like something is happening that is not really, it's totally fake. But if this was a still image, for instance, then that could work, right? Because your brain never really picks up exactly on where the lights come and whatnot. But for this one, I didn't really want to do it like this. Also, by the way, we would have to make sure that we don't go negative, because right now this can go negative, and that's why the blacks get really black over there. So we want to do it like that. So that would be one way to do it, and in many of my effects I have done it like that, and it looks pretty cool. But because here you can rotate around this ball, and so because at first I was like, okay, well I could just rotate this to kind of match the rotation, right? So I could say UV times equals the rod of T to rotate this, and then see, but now it's counter-rotating. See, like now it works from this angle onwards. It works pretty good, right? But if I rotate around, then the illusion kind of breaks very quickly. Like over here, for instance, it goes the opposite side. So yeah, so that's not the best way to do it. Now, the really expensive way to do it would be what you would really have to do in order to make it physically correct would be to take your array and to step through empty space, and for each step figure out, am I in the shade or am I in the light, and then add that light contribution, and then in the end you have many light contributions that you add up together to have your final light contribution in that direction. Okay, and you can imagine that that can get really expensive because you have to evaluate a shadow for each step. So then the question becomes, if you want to go that route, then the question becomes, okay, what are the smartest, what is the best position to take the sample so that I can get away with the least amount of samples? And so what I was thinking for that was to stick a plane inside of the ball that is camera facing. So like imagine you have a plane that goes exactly through the center of the ball, and the plane always follows the camera. So if the camera is over here, the plane just turns with it. If the camera goes up, the plane goes like that, you know. And so when you do that, and you have the 3D position of your camera array. So if I take my camera array and I intersect with that plane, now I have a 3D position, and now I can check if that 3D position is in the shade or not, and based on that I can color it one way or another. So let's try to do that. So first, what we need is a function that can give us the intersection between an array and a plane. And I'm going to just do it quickly. I should probably make a video about it at some point. For now, I'm going to go array plane. It's going to take as an input a ray, which has a ray origin and a ray direction. And it's going to take a plane, which has a point on the plane, and it has a normal direction. Okay. And now we're going to have to calculate the position of where that ray goes through the plane. And the way to do that is to take the dot product of the ray origin minus the position with my normal, and then divide it by the ray direction and the normal, and that's going to give me some value t, float t. But that value can also be negative, and if it was negative, then I would calculate an intersection behind me. But because we're not intersecting a line we're not intersecting an infinite line with a plane, we're intersecting an array, and array is one directional, and so that's why we have to clamp this to make sure that we don't get negative t's out of this. And then I can just return a value that starts at the ray origin, goes in the ray direction for t steps, and that should give me the intersection with the plane. So I hope I did that correctly. Let me see how that pans out. So for my volumetrics, I'm not going to do this thing. So let's just get rid of all of this. Actually, the center shading we can keep. So that's the mask center. Alright, and we can also still add it as well. But now, first I have to intersect my ray with my plane. So I'm going to do ray plane. I'm going to intersect the I ray. It goes from the ray origin in the ray direction. And my plane is at 0, 0, 0 at the origin. And the direction of the plane is exactly facing me, right? So, well, what is facing me? Well, that's this RO over here. Yeah. Is that correct? Yes. So I'm going to do RO, and I need to normalize that as well. So that should give me a 2D intersection, no, a 3D intersection point. So vec3, call it PP for plane point. Okay. Find plane intersection. And now we have our PP point on the plane somewhere, and now we have to figure out if that point is in the shade or not. Well, we already done that a few times. We could just use this for that. But then instead of that, we're going to check if point PP is there. And actually, so point PP might be a point over here on the plane somewhere, but we have to project that now to be exactly on the edge of the sphere as well. So we also need to normalize this again. Normalize. So when you say normalize a vector, that just makes it of length 1. And because I chose my ball to have a radius of 1, I don't need to do anything else. Otherwise, I would have to multiply by the radius of the ball. So keep that in mind. So often you want to choose your sizes and your origins for your coordinate systems in a proper way so that you can get rid of a lot of extra math. So yeah, keep that in mind. So now we have this, and now let's see here. SB. Yeah, let me just say I could call this SB. I could say Starburst. Let me see what that does. Okay, that gives me an error. Okay, this should be RD, not D. And that doesn't work, which is no bueno. Let me try to figure this out. Yeah, all right, so I just made a mistake here. This should be P minus RO, not RO minus P. Okay, and now, would you look at that? Now we have some really cool volumetrics, and let me just turn them on a little bit stronger so you can properly see. Times 2. Okay, so now we have stuff that always rotates in the right direction. You see, like over here, now it rotates in the right direction, but if I turn around, it still rotates in the right direction, which is pretty cool. Yeah, and this is also very, very cheap compared to another like volumetrics, right? Because we're only evaluating something once. There's only one call to this function in order to evaluate that thing, which is pretty neat. Now, you could make multiple planes here, because this plane is just a plane that's exactly stuck through the center. But if we wanted to do real or more realistic 3D stuff, then we could sample that on multiple planes. So not just here. So I tried that, but I didn't think it looked so good. But anyways, I'll show you how you could do it. So what you could do here, so this is where the plane goes through 0, right? But we can move that towards the camera or away from the camera. So what we could do is I could do normalize RO. If I do this times 0, right, that's the same thing. But now if I do times 1, let's say I can kind of move that plane forward or backwards. Okay, and yeah, and that might help for some things. And then so what you could do is you could multiply this by some jitter factor, and that's still times 0.2, let's say. And then I could say float jitter equals the hash 21 of the v coordinate, so that my jitter value is different for every pixel. So if for every pixel that value is different, then my plane will shift for every pixel back and forth, so we can kind of get a more correct 3D effect. But I found the change that it made is very minimal, and it introduces noise, and it just doesn't look as nice as I thought it would look. But theoretically, this should be better. So what you could do in order to get rid of the noise is do multiple samples per pixel. But I didn't really think that it added that much, so I decided to just not do it and just go with one sample for the entire thing here, which I think works pretty good. All right, so next, what are we adding here? Yeah, I wanted to add some some effect where you can look through the object a little bit when the light is behind it. I thought that could be kind of cool. So let's try to add that. So what I can do for that is to go inside of here, and then inside of here we're dealing with the floor, right? So floor material, and because we hit the floor, right? So, or we could say we hit the floor. We hit the floor. And so if we didn't hit the floor, well, then we must have hit the ball. So over here, it's hit the ball. And so for the ball, we could add something. So we could add, for instance, yeah, some subsurface scattering, which is something that would, some effect where the light kind of goes through the object. And so for that, what I could do is I could just fake something for this. So what I can do is I can check, let me see here. Let me check the length from the center of the screen. And for that, yeah. I have this here, which I should probably reuse. So let me just cut that out and put that at the top here. CD. And let me call it CDS, because over here we already have another CD. So let me call it CDS. And then over here I can use CDS, if I can find where I use it. Okay, so here, CDS, and that should work. Oh, no, over here as well. Okay, so now we have that, and now we could use that over here, because let's see here what happens if we do col plus equals CDS times some red color, because we want it to, let's say, be translucent red, as if it has blood on the inside. So I can say times 1 and 0.3 and 0.4, let's say. Let's see what that looks like. Yeah, okay, so that makes sense that it gets reddish out there, because this is just my distance. I need the inverse of that. So, so what I can do is, let me just cut this out here and call this SSS for subsurface scattering, and I can say that's 0.1 divided by CDS. So if my center distance squared gets smaller, 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 this number gets larger, 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 right? Because it's some number divided by some really small number. So, and then over here I can say plus SSS, and that's way too much. So let me just make that smaller. Okay, so now we're getting somewhere. Right now, you can see that we can see something, but now that gets way too strong. So maybe I shouldn't do it like this. But anyways, let me just see. Let me make a cap on it, so I can say SSS equals the minimum of SSS and 2. Let's say. So now I get that. Yeah, I'm not sure if this works as well as I wanted it to work, because obviously we don't want that weird step here. So let me not do 1 divided by. Let me use a smooth step for this, and then say from 0.2 to 0. You can do that. Let me see what that looks like. Yeah, that looks better. Now obviously that needs to be smaller. 0.1. Yeah, I want it to be smaller still, but maybe I can multiply this by itself in order to do that, because then the fall off is going to be nicer, I think. So SSS times equals SSS. That's still too large. Let's make it smaller. 0.5. Yeah, I think something like that could work. And let me just, maybe we want to make it a bit more reddish. Anyways, you can play with it. But that's kind of what I did for the subsurface scattering. And then to add some interest to this, I add some silhouette inside of here. And the way that I do that is by just taking another ball gyroid reading, because that reading gives me the distance to this shape, right? And I can make use of that. So what I can do over here is I can say that, and then give me the ball gyroid of point P, which is the pixel on the surface that we're evaluating right now, and then we see how far away that is from the object, from the infinitely thin object in the middle. And then I could multiply my subsurface scattering by that value. And I probably have to cut that out somehow, so let me see here. Now, okay, so on the inside, we're on the inside of this now, so this should be negative, I suppose. Yeah, okay, so now I have something, and now I turn these ones around. 0. Okay, so now I have a dark line. Let's make it thinner. No, hang on. Yeah, so make it a little bit thicker. Yeah, so that gives some idea that there's some structure inside of this. And now to make it a bit more interesting, what we can do is we could wiggle this around a little bit. And the way to do that is by just wiggling the input position a little bit. The way I can wiggle the input position is I could, for instance, just add a sign to it, and then the sign of the same position times 10, let's say, and then that's going to be way too much of a wiggle. Yeah, although that could maybe also be cool. Although this gets projected on the surface, so you have to be kind of careful with what you're doing here, or you're kind of losing the effect. So let me make this a lot smaller, and even smaller still. Okay, and now let's add time to that so that it moves. Okay, so now let's see if we can catch it. So now we have a structure inside that is moving. You see? It's a bit hard to see because my lights are a bit big, but there you go. So yeah, so anyways, that's kind of the idea, and I know for the final effect, you need to just tweak stuff until everything looks perfect, but I think for now this could be good. So now let me add one little thing here that often makes things look a lot nicer, which is a simple vignette. And in order to make a vignette, I can say call times equals, let's say, well, if I do the center distance squared, then it's going to be dark in the middle and brighter on the outside. I want the opposite of that, so I can just do 1 minus. And now it makes the outside dark and the inside bright. So before it was like this, and now it's like this. And you can make that softer. You could multiply this by some smaller than 1 value to kind of attenuate that a little bit. But yeah, that's kind of it. Maybe we also want to rotate the camera slowly as well. So over here is my left-right rotate. Over here I could add T to that so that we slowly rotate. And then maybe we want to do that slower. And so now we have basically the finished effect. So yeah, like I said for the other effect that I did, it's just a bit more, like everything is a bit more tweaked, but this is basically it. One thing that I was trying to do on my effect that I didn't finish yet or didn't manage to do properly, something that if you made it this far, maybe you want to give it a try, is to have an imprint that the ball leaves on the sand. That would be really cool. So when the ball rolls, I would like to see an imprint here of exactly what it pressed into the sand. And so the way that you would do that is you would have to make a function that takes a linear position along a line and it wraps it around the circle to see, or around the sphere to see where that, to which part of the sphere that maps, right? If you can make a function that takes a flat position and it maps it to some point on the circumference of the sphere, and then you evaluate the gyroid over there, and then you know whether it should be depressed or not, similar to how we used sampling that function for figuring out the shadows, for figuring out whether the light in the center shines in your eyes or not, and also the volumetrics, right? So that could be used for that as well. So yeah, if you haven't checked out my video on gyroids yet, I highly recommend you do. It's a very powerful thing that you can use for lots of different cool looking things, not just this. So yeah, so if you want to look more into that, then I would recommend you check that out. Anyways, I hope you liked this, and I sincerely hope you click subscribe. It doesn't cost you anything. You can always unsubscribe later if you decided that this is not for you, but it helps me out a lot. So please click subscribe, click like, leave a comment, and stay awesome. And I hope to see you next time.